All right, time for some more quantum mechanics. Today we're going to continue our conversation about how we compare two or more angular momentum, and this time we're going to do this by returning our focus to spin states. So, when we're working with a system with multiple unpaired electrons, we often want to determine the total angular momentum that stems just from the electron spin. So, we're going to do this by focusing in on a property called the total spin quantum number. This is capital S, which can be determined from using a Clebsch-Gordan sequence of the combinations of unpaired electrons, where the total spin can be essentially, will max out at the two spins added together and minimize when they are directly opposed. Now, this is the same basic idea we used for orbital angular momentum, but now we have a major advantage, which is, in this case, every electron has the exact same spin state, and that's 1/2. So if I'm dealing with a simple two-electron system, this becomes much easier than for our orbital angular momentum, as we have two possibilities. Either the two spins can add together, and we're going to have a total spin number of 1, or our two spins can be opposed, and they will have a minimum value of 0. So for this case, this is great. In fact, we've already done this problem before. These are our old friends, the singlet and the triplet state. But where spin can often get a little bit more confusing is as I go to multiple unpaired electrons, so more than 2. So we can do this problem by using our Clebsch-Gordan series, and now we can start with our, say, 2 unpaired electrons, and they can have one of 2 states. And if I want to examine what happens when I add in a third electron, what we can do is use our Clebsch-Gordan sequence and pair our third electron with one of our previous states. So let's look at the maximum value. I can take an extra electron and I can pair it with my S1 state. And it will have one of 2 possibilities. Either all 3 electrons will be pointed in the exact same direction, and so I'll have a total spin number of 3/2, or one of them can go in the opposite direction, and I can have a total spin of 1/2. Now, if I have 2 electrons going in the opposite direction, well, we don't care about direction yet, so that's still 1 electron going in the opposite direction. So we only have 2 options here, a 3/2 or 1/2 total spin. Again, being completely dictated by the number, how many electrons are being opposed to the net direction. So we can then extend this idea on further to a 4-electron state, which will have a maximum total spin of all 4 electrons pointed in the same direction. So I just tag on an extra half with my Clebsch-Gordan series, and we'll have a maximum value of 2. And then we can use, again, these same ideas of Clebsch-Gordan, and I'll have possible total spin numbers decreasing by integer values of 1 and 0, and again, no negative values possible. And we can keep extending this idea even further. So if I have 5 unpaired electrons, my total spin is, lo and behold, 5/2, with alternate values of 3/2 and 1/2 if I have 1 opposed spin or 2 opposed spins. And so we can keep extending this idea. And so this isn't actually too bad of a concept to play around with, and a lot more friendly than our orbital numbers. But as always, we often care about what direction the spin is pointed, and specifically, we often denote this by looking at just the z direction. So we are going to bring in our old friend, a magnetic quantum number, and this time, of course, it's the spin magnetic quantum number, which I believe we've seen before. So this is going to be the value, depict the extent of the spin just in the z direction. And we'll have values, just like its lowercase version, ranging from negative of the spin all the way up to the positive value of the spin, where we start with all of the spin pointed against the z-axis, all the spin pointed with the z-axis, and some variance in between where it's pointed off in different directions. So we've also already addressed some of these ideas before, and in fact, we've even seen their wave functions when we dealt with the singlet triplet state. So for a little bit more detail, feel free to go back to that video. But the major idea is that if I have two unpaired electrons and I have a maximum uh, total spin number of 1, I can either have both of my spins pointed up, both of my spins pointed down, or one spin pointed up and one spin pointed down, but I still have a net angular momentum. It's just now going in the xy axis, which brings me to a very important point, which is that um, the values of our total spin quantum number don't have to be equal to the value of s. So if I have an s of 1, I can have a magnetic number of 0. And just because I have a magnetic number of 0 where one electron is up and one electron is down doesn't mean that their spins completely cancel. They can still be aligned in some other direction than the z. But similarly to when we are working with orbital angular momentum, this directional magnetic property can still give me some useful information about my total spin. And that's simply the fact that if I have a maximum m sub s of 1, it turns out that I can't have a total spin greater than that value. Because if my maximum directional spin is 1, that means that's also my maximum spin. And we'll be taking advantage of this property later. But for now, it's useful to know that while a value of 0 doesn't mean you can't have doesn't mean you belong to the total spin of 1, a maximum m sub s of 1 does mean your maximum s is that same value. So it's a little confusing, but hopefully as we go forward through the next couple lectures, this will make a little bit more sense. So one of the other important things to note when we're talking about total spins and directions is that most people don't actually use the total spin number. Instead, it's much more typical that people refer to the multiplicity. So the multiplicity is just going to be the total, twice the total spin of the system plus 1. So the major advantage of taking twice the total spin is that we get rid of all of our typical fractions, which are often 1/2 or 3/2. And then the 1 value helps bring us to a logical sequence of possible multiplicities of 1, 2, 3, and 4. Now, what's important to note is that each of these multiplicities does have an associated name, and some of these are going to sound fairly familiar. So if my system is completely paired up and I have a total spin of 0, then my multiplicity is 1, and we call this a singlet state. Now, if I have a single unpaired electron, this gives me a multiplicity of 2, which is a much nicer value to deal with, and gives us our classic name of doublet. And then we've seen this one before. If you have 2 aligned spins, this is going to give you a multiplicity of 3 and a triplet state. And this will continue as I increase through my numbers of unpaired electrons, and our multiplicities will subsequently go through triplet, quartet, quintet, sextet, septet, octet, nonet, and decet. So those of you who are into music, those will sound familiar. For the rest of you, we often don't get to those higher numbers unless we're playing around a lot with metals. But one of the important things to note when we're talking about multiplicities is that in general, I'm going to want to occupy the highest available multiplicity, as this tends to be energetically favored. And this is an idea we already brought up in the lecture on singlets and triplets. And this is largely due to the fact that spin pairing energy will be greater if I have a lower spin state, because when my electrons occupy uh, different spins, they can get a little bit closer and have a higher degree of repulsion. If my spins are all aligned, it means everybody stays out of each other's way and they can spread out. And this tends to be energetically favored. Now, there are definitely some properties that will drive against this trend, but it often is going to depend heavily on environment. So when working with gas-phase systems, generally, if I have a 3 unpaired electrons, I'm going to tend to 4 unpaired electrons, I'm going to tend to favor the quintet over a triplet or a singlet state. So we can use all of these rules we've now developed uh, for our total spin quantum numbers, our multiplicities, and our possible magnetic quantum numbers for atomic systems, and talk about some real cases. So let's go ahead and start with a excited sodium atom, which will have a single electron in the p orbital. So in this case, we will have a single unpaired electron. So this gives us a total spin of 1/2. We don't have to worry about any pairing. And this is a doublet system. And that single spin can either be aligned up or down with magnetic numbers of 1/2 or -1/2. So then we can make the system a little bit more entertaining. We can go to 2 electrons for an excited state magnesium with 1 electron in the s orbital and 1 electron in the p orbital. So in this case, our 2 electrons can either be aligned in the same direction or opposed, which gives us total spin numbers of 0 or 1. So this is our old friends, the singlet or triplet state. And this gives us our magnetic numbers of -1, 0, or 1. Now we can extend this idea a little bit further, deal with an excited state aluminum atom, where I have a single electron in an s orbital and 2 electrons in the p subshell. So in this case, all 3 electrons can be pointed in the same direction for a maximum total spin of 3/2, with of course another option of a total spin of 1/2. And this corresponds to our doublet or our quartet states. Now, at this point, our potential magnetic spin numbers get a little bit out of hand with values ranging from -3/2 to 3/2. Though it is worth noting that if you have an odd number of electrons, you tend to not have a possible singlet state. So this is, or a magnetic quantum number of 0. So this is important because it does tell us that if I have an odd number of electrons, I will definitely exhibit a magnetic moment, which can be very important when you're looking at the physical properties of various elements. So that brings us to the end of today's lecture on spin. Next time, we're going to be looking at how we compare our total spin numbers and our total orbital angular momentum numbers together to look at an entire atomic species. So take care and stay safe.